Hello everybody and welcome to ATC Maths and Science. Today we'll be discussing how to determine the equation of a cubic graph using given x-intercepts. Now, we're usually given the x-intercepts plus one other point that lies on the graph. Now, we will see the purpose of having another point on the graph shortly. But what we're going to be doing now is using one of two equations. Now, the equation that we're going to be using depends on how many x-intercepts are given to us. So we have f of x is equal to a into x minus x1 into x minus x2 into x minus x3, and we use this formula when we have three distinct x-intercepts: x1, x2, and x3. The second equation will be used when we have two distinct x-intercepts. So f of x is equal to a into x minus x1 into x minus x2 all squared. Now, how can we have a cubic function that has just two distinct x-intercepts? Well, it happens when the turning point is both a turning point and the x-intercept. But what we must be very careful of when we're substituting into this equation, that the bracket with the squared has to contain the value that is the x-intercept, the turning point x-intercept. Right? So let's look at an example on how this would work. And our major decision, firstly, will be whether to use equation 1 or whether to use equation 2, depending on what our given information is. So let's say, for instance, this was the example that we're looking at. So here on our Cartesian plane, we'll have a cubic graph, and let's say we've got minus 3, minus 1, and 2. And we just need any other point that lies on the graph. Let's say this point here is 0 and minus 6, right? So we have three distinct x-intercepts. Therefore, we will use the formula f of x is equal to a into x minus x1 into x minus x2 into x minus x3. Firstly, we need to substitute our x1, x2, and x3. So it's x minus minus 3, which then becomes plus 3, x minus minus 1, which is plus 1, and lastly x minus 2. Now, this is where the other point that lies on the graph, its purpose becomes clear. We need the value of a, because what we would like to do is multiply this entire equation out so we can get our equation in its standard form. But in order to multiply this entire equation out, we need the value of a. So we take the other point that lies on the graph, which is 0 for x and minus 6 for y, and into our equation, wherever we see an x, we'll replace it with 0, and wherever we see y or f of x, we'll replace it with minus 6. So we have minus 6 is equal to a into 0 plus 3 into 0 plus 1 into 0 minus 2. So minus 6 is equal to, simplifying all of this, we get a is equal to 3 times 1 times negative 2. So minus 6 is equal to minus 6a. Therefore, a is equal to 1. Now that we know that the value of a is 1, we can take this, substitute it back into this equation, replace a, and then now multiply the whole thing out. So we have f of x is equal to 1. We don't have to write it, we can leave it as an invisible 1, to x plus 3, x plus 1, x minus 2. So multiplying the first, or the last two brackets first, this would give me x squared. So I'm multiplying it and adding like terms all at once. So this will give me x squared minus x minus 2. And then finally, we'll have to multiply the third bracket in. And so we have f of x is equal to x times x squared is x cubed, x times minus x is minus 2, minus x squared, 3 times x squared is 3x squared, so this gives me plus 2x squared. X times minus 2 is minus 2x, 3 times minus x is minus 3x, so that will result in minus 5x, adding the like terms, and then 3 times negative 2 is negative 6. And we now have the equation of our cubic graph. So this was an example where we used the first of the two equations. Let's see an example where we're using the second equation, but this time round let's give the example a little twist. So as we notice, we need to be given either 2 or 3 distinct x-intercepts and another point that lies on the graph. And the purpose of the other point, as we saw in the previous example, is in order for us to find the value of a. But sometimes they will not give us that other point, and so we must note where we will get the value of a from, right? So this example will be such an example. So let's say we have the equation f of x is equal to minus x cubed plus ax squared plus bx plus c, and we want to determine the values of a, b, and c, and this is what we're given in the question. So and we're told that this is minus 2, and we're told that that's 3, and that's all we're given, just 2 x-intercepts. So since we're given 2 x-intercepts, we know we're going to be using the second equation. So f of x is equal to a into x minus x1 into x minus x2 all squared. And we'll substitute into this equation like we normally would. So f of x is equal to a into x. Now notice which value goes into which bracket. It's x minus 3, because that's not the turning point. The turning point x-intercept goes into the squared bracket. So it becomes x minus minus 2, which is plus 2 all squared. Normally, we would take another point that lies on the graph, substitute for x and y, and solve for a. We don't have another point that lies on the graph. So what do we do now? We will find the value of a in the question itself. You see, the standard equation of a cubic graph is, it looks as follows. The standard equation is ax cubed plus bx squared plus cx plus d. This is where that a comes from in this equation. So we can see now clearly that the value of a is negative 1, right? So we don't have to actually go ahead and solve for it. So now we have f of x is equal to negative 1 into x minus 3 into x plus 2 all squared. We can square the last bracket. So negative into x minus 3 into x squared plus 4x plus 4. Then multiplying the two brackets, distributive law, and I'm not going to show adding the like terms, I'm just writing down the answer. So we have x cubed plus x squared minus 8x minus 12, and finally we can multiply our negative into the bracket, so we get minus x cubed minus x squared plus 8x plus 12. So we can see clearly the value of a is negative 1, b is 8, and c is 12. And that is the use of the two formulas for determining the equation of a cubic graph using x-intercepts.